After we created our neural network, the next goal is to create the loss function and the optimizer. It is little different compared to Keras in PyTorch. So for the criterion, which is the loss function, we'll write torch.nn and mean squared error loss. And for the optimizer, what we have to do is we have to first pass all the trainable parameters of the model. So model.parameters, we have to pass it, we give it as an input to the optimizer Adam, and we have to specify the learning rate as well. So now we'll start the training of the neural network. But before training, let's just do for one epoch. What will happen? We basically want to take samples from our data loader and put it through the model and calculate the loss function. Then using that loss, we want to backpropagate through our network and using the backpropagation algorithm, we want to optimize the weights of the autoencoder model that we have. That's all we want. So let's do that. So first goal is to loop through our data loader. We'll iterate through the train loader, and this image will basically take a batch of images. So when you write image.shape, we get 16 batches of images. Alright, and this one is basically the corresponding label, but we do not require the label, so we don't need it. We don't need to operate on it. Alright. And then what was our next goal? Next goal is to pass it through our model to have an output. So this is the reconstruction basically. Because it is model is an autoencoder, whatever we pass, the same thing should be the output. And then we need to calculate the loss function, the criterion object from the torch.nn.msc loss. This basically calculates the loss between the output and the target, which is our actual image. So when we do loss.backward, it does the back propagation and calculates the derivative of the gradient. And in the last step, what we do is optimizer the step. So what does this optimizer dot step does? It, after the gradient are calculated in this part, it basically uses those gradient to update the weights. That's it. So our one loop is done. So if you run this, it should work just fine. Yeah. So right now our just one single batch is well processed. It is trained through our neural network. But there are some two nuances that you need to focus on when you are using PyTorch for training. One of the thing there is to use optimizer.zero grad. So why this is necessary? This is necessary because whenever you do loss.backward, the derivative of the weights are always saved in a particular variable, and if you do not do optimizer.zero grad, they keep on accumulating. That means they keep on adding up. So that's why you need to do optimizer.zero grad in order to avoid this issue. This is the loop for just one epoch, but we want to do for at least like 50 to 100 epochs. So for that, what will we do? We'll write a. So now our training loop is completed. It will basically, our model will be trained for 100 epochs. But here one problem is this entire thing is happening in the CPU. So one way, and it will take crazy long time. So if you want to estimate how long it will take, you can use something called as TQDM. So let me give you what TQDM can do. So yeah, so what I did is I used this TQDM basically gives you a progress bar, which is nice to look when there is a big process going on behind. So if I run this, it will basically estimate how long it will take to train for 100 epochs on the CPU. So I'll just fast forward at this point. So what we see here is when we train on the CPU, it takes around 3 hours, 24 minutes to train for 100 epochs, which is too much. So in case you have a GPU, or you can access the Google Collaboratory where the GPU is uh, available for free. So you should take advantage of that. So right now I'm going to stop this CPU implementation and I'm going to show you how you can do this using the GPU. So to take our model to the GPU, it's a very simple thing. We just have to write model.cura. This will move our model to the GPU. All right, and you remember to put this model.cura before the optimizer, because the optimizer takes model.parameters which should be in the GPU. All right, and then coming to our training loop, we have to do a small change in the training loop as well, because as we took our model to the GPU, and the dot product of the weights with the input has to happen in the same device, we need to change our the device of our input to the GPU as well. So for that, as we are operating on the image, we just have to do image equal to image.CUDA. So this will send our image to the GPU, and that's it. Now we can just run this. So before we saw that with the CPU, it took around 3 hours, but with the GPU, it takes uh, almost 1/3 of the time. That is one advantage. Now I'm going to stop this training because I've already done the training and I saved the model. I've saved the model. But let's see, one another thing is how we can improve this training loop. So right now we do not have any live update that what is our loss, whether our loss is decreasing, increasing, and we do not know about overfitting and underfitting. So what we can do is we can also create a loop for the validation loss. So we can keep track of it. And how we are going to do that? Yeah, so now I'm just going to replace this with this file. So it's more or less the same. So this part up to this is the part that we just saw. What extra is happening here is this. I'm creating two different lists to keep track of my actual loss and my validation loss. So this is the extra loop that I have created for the validation loss. That's it. And after every 5 epoch, I'm printing my current loss and the validation loss just to keep track if there is an overfitting or underfitting. And now if I run this, we'll see the performance and also the log of the training so that we can stop the training if it started overfitting. So yeah, now we can see that after 5 epochs, the loss is slightly decreased. That's all we wanted. Now I'm going to stop the training process because I have already done the training. And yeah, one more important part, except for training, is how we can save and load the model whenever we need. So for that, what we are going to do is we are going to do torch.save, and then we are going to do model.state directory. So this will basically save the weights as a dictionary. So and we of course you give the name in which name you want to save, and the extension has to be PTH. This is the PyTorch file. So you see I already saved it here, and then when you want to load it back, you can just do this. So right now I'm going to comment this one out, and I'm going to run this. So what happened is all keys match successfully. That means all the keys of this dictionary match successfully with the model. And one thing to note here is first you have to create the model structure first. So what I mean is before doing this load state directory, you have to call this basically the structure of the model with all the weights randomly initialized. Then you use the state dictionary to load the trained weights. All right, that was about it, and that was all about this video. I have also given this trained model so that you can replicate without training your model the results. Right. So yeah, in the next video, we'll try to visualize the output of the trained model, and also we'll establish a metric to evaluate the anomaly detection algorithm.